It is like funny how quickly a marvel of modern engineering can just turn into a massive headache.
Oh, absolutely. It happens all the time.
Right. Like you set up a pristine Kubernetes cluster, you deploy your apps, everything scales beautifully. And then, you check your cloud bill.
Yeah, and suddenly you realize your state-of-the-art infrastructure isn't just serving your customers.
Nope. It is aggressively mining cryptocurrency for some hacker on the other side of the world.
Which is just a devastating realization.
It really is. So, welcome to this deep dive. We are looking at a massive stack of sources today. Post-mortem security reports, architecture white papers, and a pile of study guides for the KCNA exam.
Right, because our core mission here is mastering Kubernetes security fundamentals.
Exactly. Specifically for you, if you are gearing up for that exam, or, if you were just trying to make sure your own cluster doesn't end up funding someone's early retirement.
Because that cryptocurrency scenario, it happens because a cluster is fundamentally just this incredibly powerful distributed compute engine. Like, if you leave the keys in the ignition, someone is going to drive it away.
Yeah, they're taking the car.
Exactly. So to understand how to secure it, we really have to establish the single most critical fact of Kubernetes architecture.
Which is the API server, right?
Yes. The kube-apiserver is the single entry point to absolutely everything. It is the brain.
Like everything flows through it.
Every command you run, every pod that gets scheduled, every internal component talking to another internal component, it all goes through this one central hub.
Okay, let's unpack this. Because right away, the sources highlight a major distinction that you really need to master.
The two phases of the security check.
Right. When a request hits that API server, it doesn't just evaluate it in one go. It splits it into authentication, or authn, or authorization, or authz.
Yeah, and people mix those up constantly.
They do. I was trying to conceptualize this. And it feels a lot like a bank teller system.
Oh, the bank teller analogy works perfectly here.
Because, when you walk up to a bank teller, the very first thing they ask for is your ID and your debit card.
Right. That is authentication. You are just proving who you are. The teller verifies your signature or, your PN.
But just because you have a valid ID doesn't mean you can ask the teller to withdraw $1 million.
Exactly, because the teller turns around, looks at the bank's back-end system, and checks your actual account balance.
Right. My balance dictates what I am actually allowed to do. And that back-end check, that is the authorization.
And the fascinating thing is Kubernetes handles these two processes entirely separately.
Really? Entirely?
Yeah, it relies heavily on external systems for the authentication piece.
Like what kind of systems?
Things like OIDC providers, Cloud IAM, or TLS certificates. Kubernetes basically says, hey, I trust this external system to verify your ID.
Okay, so it outsources the ID check.
Exactly. But once that ID is verified, Kubernetes takes over completely for the authorization phase.
Oh, I see.
It checks its own internal rulebook to see if your verified identity is actually allowed to, say, delete a database or scale down a web server.
So if Kubernetes handles the rulebook, how do we actually write those rules? Reading through these manifests, it just feels like a wall of text.
It can definitely look like that at first.
Yeah. How does the system actually organize these permissions under the hood?
So the sources point directly to RBAC, role-based access control.
Okay, right.
And the architecture of RBAC is built on separating the definition of a permission from the assignment of that permission.
Okay, so like creating an office keycard system?
Yes, exactly. Think of RBAC as the building's access control.
Okay.
First, we define what doors actually exist using a role. A role is simply a list of roles.
So the role is the specific permissions.
Right. But, and this is a critical boundary, a role is strictly scoped to a specific namespace.
So it's fenced in.
Yes. If you create a role in the accounting namespace, those rules physically cannot interact with anything in the engineering namespace.
Okay, so a role is inherently fenced in. What if I want a rule book that applies to the entire building, the whole cluster?
Then you need a different object. You need a cluster role.
Okay, role for the namespace, cluster role for the cluster.
Exactly. The cluster role is for permissions that transcend namespaces.
Like what?
Like allowing a monitoring tool to view the health of nodes, or giving an admin the ability to manage storage classes across the entire infrastructure.
Okay, so we have our two types of roles, our roles and our cluster roles. How do we actually hand those out to people, like handing out the key cards?
We use bindings.
Bindings, okay.
The role binding takes a role and attaches it to a user or an identity within that specific namespace.
Makes sense.
And the cluster role binding takes a cluster role and attaches it to a user across the entire cluster.
Got it. So there are 4 core objects you really have to know here. Role, cluster role binding, and cluster role binding.
Yes, those are the 4 pillars.
I want to look closer at the actual rules inside those roles because, the exam guides focus heavily on the verbs.
The verbs are crucial.
Yeah, the actions you can take. I assume we shouldn't just be blindly memorizing a list of words like get, list, watch, create, update, patch, delete.
No, you need to understand why they are separate.
Right, like why does Kubernetes separate these actions so granularly? For instance, why treat get and list as 2 completely different permissions?
It really comes down to beta exposure.
How so?
Well, get allows you to request one specific named object. If you know the exact name of a pod, you can view its details.
Okay, so I need to know the name already.
Exactly. But list allows you to ask the API server to show you absolutely everything in a namespace.
Oh, wow. So list is like asking for the whole directory.
Yes. And from an attacker's perspective, list is a reconnaissance goldmine.
That makes total sense. Reconnaissance is the first step of a breach.
Right. If they breach an account with get permissions, they have to blindly guess the names of sensitive resources.
Which is super noisy and difficult.
Exactly. But if they have list permissions, the API server just hands them the entire map of the environment on a silver platter.
Okay, I also noticed the sources draw a big line between update and patch.
Yes, those are very different mechanically.
If I want to change a pod, why does it matter which verb I use?
To use the update verb, you generally have to provide the entire complete manifest of the object to replace the existing one.
Okay, so it's a full swap.
Right. But the patch verb is surgical.
Surgical how?
You can send a tiny payload that alters just one single field.
Oh, like just changing an image tag.
Exactly. You could change the image tag of a container from your web application to a cryptocurrency mining image without needing to know or supply the rest of the complex configuration.
Wow.
Because patch is so stealthy and easy to execute, security teams heavily scrutinize which identities hold that verb.
Okay, here's where it gets really interesting.
Yeah.
Because in these study guides, there's a specific scenario that keeps popping up.
The exam trad.
Yes, it is a massive trap for exam takers. It involves mixing these scopes.
Right.
What happens if you take a cluster role, which we established as a cluster-wide rulebook, but you bind it using a standard namespace scoped role binding?
The counterintuitive truth is that the role binding acts as a constraint.
Wait, really? It overrides the cluster-wide part.
Yes. If you bind a cluster role with a role binding, those permissions are instantly restricted to only apply to the namespace where the role binding exists.
Why on earth would the system be designed to allow that? It seems like it exists just to confuse people on a test.
It does seem like a trick, but it is actually a powerful feature for centralized management.
Centralized management? How?
Imagine you have a standard developer view policy that you want 50 different developers to have,
Okay.
but you only want them to have it in their own personal namespaces.
Right. I don't want them seeing each other's stuff.
Exactly. If you used normal roles, you would have to maintain 50 identical copies of that rulebook across 50 namespaces.
Oh, that sounds like a nightmare. If I need to add a permission, I have to update 50 objects.
Precisely. So instead, by creating one cluster rule, you maintain a single centralized rulebook.
Okay.
Then you use 50 namespace scoped role bindings to apply that single rulebook to the 50 different namespaces.
Oh. So the rules are centralized, but the access remains perfectly isolated.
Exactly.
So the role binding acts like an anchor, pulling that massive cluster-wide rulebook down into a single fenced yard. That is actually a brilliant design.
It is, once you understand the mechanics.
Now, let me throw a scenario at you, because I've actually been in this situation.
Okay, let's hear it.
Let's say I'm a developer at an internal startup. We're moving fast. I deploy a new application, and it needs to query the API server to check the health of some other pods.
Pretty common requirement.
Yeah, but I keep getting authorization errors. I am under a deadline.
Of course.
Spending 3 days meticulously crafting least privilege RBAC rules, figuring out if I need list or get or patch. It just feels like massive overkill for an app that just checks health status.
I see where this is going.
Why can't I just grant the cluster admin role while we are in beta, get the app working, and then lock it down later?
If we connect this to the bigger picture, the problem with locking it down later is that The blast radius of that shortcut is catastrophic.
Catastrophic. Isn't it just inside the cluster?
When you grant cluster admin to an application, you aren't just making it easier for the application to run.
Okay, what am I doing then?
You are handing the keys to the entire pingdom to anything that manages to execute code inside that container.
Walk me through the mechanics of that. Let's say my web front end has a vulnerability, a standard remote code execution flaw.
Okay, a standard RCE.
The attacker gets in. What exactly are they doing to leverage that cluster admin permission? The API server doesn't know it's a hacker?
Right, the API server just demands an ID.
So how does a piece of rogue code prove who it is?
This is where we transition from human identities to robot identities.
Robot coup cards.
Exactly. When a pod is scheduled, Kubernetes physically mounts a cryptographic token into the pod's file system.
Wait, it just puts a file on the disk?
Yes. Usually at varinsecretskubernetes.io service account.
That's a mouthful.
It is, but that token is the pod's ID card. It is called a service account.
Okay, so the pod has an ID card file.
Right. And when your application talks to the API server, it reads that token from the file system and attaches it to the request.
So if the attacker gets remote code execution, they can just read that exact same file path.
Precisely. They run a simple cat command on that file path, extract the token, and suddenly they're your application.
Oh, wow.
If you gave that service account cluster admin to save time, the attacker now has a token that allows them to delete production databases, pull TLS certificates, read password.
Just from running a cat command.
Yeah, and they can spin up hundreds of high CPU pods for crypto mining. The API server looks at the token, sees cluster admin, and executes every malicious command without hesitation.
Which means the identity isn't tied to the code we wrote.
No, not at all.
It's tied to the environment the code is running in. That is terrifying.
It really is.
What if I don't assign a service account at all? I just deploy a standard pod. Does it have no identity?
Kubernetes always assigns an identity.
Really? Even if I do nothing?
If you don't explicitly specify a service account, the pod is automatically assigned the default service account for that namespace.
I'm guessing relying on that default account is exactly what the security white papers are warning against.
It creates a massive lateral movement risk.
Because everyone is using the same ID.
Exactly. If every pod in a namespace uses the same default identity, they all share the exact same permissions.
Oh, I see.
Imagine you have a highly secure payment processing pod and a simple internal testing tool running in the same namespace.
Okay, typical setup.
If you grant the default service account permission to read secrets so the payment pod can function...
Then my testing tool suddenly has the ability to read payment secrets too.
Exactly. And if an attacker compromises the low security testing tool, they inherit the high security permissions.
So the fundamental exam pattern here is the principle of least privilege.
Yes, always.
Every single application gets its own dedicated service account, and we meticulously map out only the verbs it actually needs.
That is the only secure way to do it.
But let's look at this from another angle.
Okay.
We've locked down the API server. Our RBAC is tight. Our service accounts are scoped. What if the attacker completely ignores the API server?
Ignore it how?
What if they exploit that web vulnerability, get inside the container, and instead of trying to talk to Kubernetes, they just try to attack the underlying Linux server hosting the pod?
Ah, well, that requires defense in depth.
Right.
We have to secure the boundary of the container itself, and that is handled through pod security contexts.
Okay, so hardening the inside.
Right. We have to remember what a container actually is at the operating system level.
It's not a virtual machine, right?
No, it is not a virtual machine. It is just a set of isolated Linux processes sharing the host node's kernel.
I see the security checklist in our sources,
Mm-hmm.
and the first major recommendation is setting run as non-root.
Yes, crucial setting.
But I always thought containers were totally isolated boxes. If I'm the root user inside my own isolated box, why does it matter?
Because of how Linux maps user IDs.
How does that work?
Historically, if you were the root user inside a container, your user ID was 0.
Right.
The root user on the underlying host server also has user ID 0.
Uh-oh.
Right. If a vulnerability allows an attacker to break out of the container's isolation boundaries, which is a container escape,
Yeah.
and they are running as user ID 0 inside the container, the host operating system might just see them as user ID 0 on the host.
Wow.
They instantly have kernel-level access to the entire server hardware.
So setting run as non-root physically forces the container engine to assign a random, unprivileged user ID to the process.
Exactly. Even if they break out, the host server just sees them as a nobody.
It strips away the most dangerous privileges before the container even starts.
It is a massive risk reduction.
The next item on this checklist is read-only root file system.
Huh?
Walk me through the mechanics of how making the disk read-only actually stops an attack.
Think about the cryptocurrency mining scenario we talked about.
Right.
An attacker exploits a web vulnerability, but to start mining, they need the actual mining software.
So they had to download it.
Usually, yeah. They execute a script that downloads a binary payload, like xarrig, saves it to the local disk, and executes it.
But if the root file system is read-only,
The operating system blocks the right operation.
the payload just cannot be saved.
Exactly. The attacker might have code execution, but they have nowhere to put their malware.
That is incredibly elegant. You aren't trying to detect the malware. You are just removing the physical capability to store it.
It effectively neutralizes entire classes of automated attacks.
The third setting here is allow privilege escalation set to false.
Yes.
What OS level mechanism is that interacting with?
It interacts with a Linux feature called the Situid bit.
Situid bit.
Sometimes non-root users need to run a command that requires root permissions,
Like what?
like changing a password using the password command. The Situid bit allows a program to temporarily run with the privileges of the file's owner, which is usually root.
Okay, I see how that could be dangerous.
Very. If an attacker finds a vulnerable binary in your container that has the Situid bit set, they can leverage it to escalate their privileges back up to root.
Which totally bypasses our run as non-root control.
Exactly. So setting allow privilege escalation to false nadir another instructs the Linux kernel to flat out deny any child process from gaining more privileges than its parent.
It neutralizes the Situid bit entirely.
Yes.
Okay, so we've crippled the attacker inside the container. They aren't root, they can't save files, they can't escalate privileges.
Right, they're stuck.
But what if their goal is simply to pivot? What if they want to scan the internal network and find a vulnerable database pod?
That is a very real threat.
So what does this all mean for the network traffic inside the cluster?
Well, by default, Kubernetes network policy is completely flat and completely open.
Totally open.
All pods can talk to all other pods across the entire cluster, regardless of what namespace they reside in.
So by default, the clusters is like a giant open plan office where everyone can shout at everyone else.
Yes.
But worse than that, it's an open plan office where everyone is wearing noise-canceling headphones, so nobody notices the malicious actor in the corner systematically checking the locks on every single filing cabinet.
That is a highly accurate way to visualize it. If they compromise your front-end web pod, there is no default network barrier stopping them from pinging every IP address in the cluster until they find your unauthenticated internal cache server.
How do we build walls in this environment?
We implement network policy objects.
Network policy, okay.
These act as an opt-in internal firewall. The moment you apply a network policy to a pod, that pod's default open status is revoked.
Oh, so it becomes isolated.
Fully isolated. And the underlying network fabric will physically drop any packet that isn't explicitly allowed by your policy rule.
And looking at the exam requirements, we need to understand the directionality of these rules. Ingress and egress.
Yes. Ingress controls incoming traffic.
Okay.
If you have a database pod, you write an ingress rule stating it can only receive connections from the specific service account of your backend API pod.
Makes sense. And egress is outgoing.
Egress controls outgoing traffic. You write an egress rule for that backend API pod stating it is only allowed to initiate connections to the database and, say, a specific external payment gateway.
So if the pod is compromised and the attacker tries to download their malware from an external server,
the egress policy blocks the outbound request at the network layer.
This has been a phenomenal breakdown. Let's recap what we've unpacked from these sources.
Sounds good.
We started at the front door, understanding that the API server separates authentication, proving your identity from authorization, checking your account balance in the back end.
And then we explored the mechanics of RBAC.
Right, learning how roles are fenced into namespaces while cluster roles span the system, and how that heavily scrutinized patch verb is vastly more surgical and dangerous than an update.
We also navigated the exam trap.
Yeah, realizing that binding a cluster role with a role binding restricts those massive permissions to a single namespace.
We dove deep into robot identities, too.
Understanding how service account tokens are physically mounted into pods, And while relying on the default account creates massive lateral movement risks.
Right.
And finally, we move to the OS layer, utilizing pod security context to force non-root user IDs, lock down the file system, and disable privilege escalation.
And we threw up network firewalls, moving away from the default open plan office by strictly defining ingress and egress traffic.
We have basically built an incredibly hostile environment for an attacker.
We have, but this raises an important question.
No.
Everything we have discussed today is deterministic. It relies on checking roles and blocking actions.
Right.
But what happens if an attacker steals a valid service account token and uses it to execute completely authorized commands, but with malicious intent?
Oh, wow.
How do we audit or detect when a perfectly authenticated, correctly authorized identity suddenly starts behaving anomalously within its legally allowed permissions?
That is wild. So it means static rules are just the foundation. If the keycard works and the network path is open, RBAC thinks everything is fine.
Exactly.
You are talking about the next evolution of security, behavioral anomaly detection.
It is the next frontier.
And that is exactly what you should be mulling over as you continue your studies and build your clusters. Because configuring the locks is the first step, but watching how the keys are actually being used is the real challenge. Thanks for joining us on this deep dive into Kubernetes security. Keep questioning those defaults, and we will catch you on the next one.